Welcome to the Deep Dive, where we deliver the knowledge straight from the source. Today, we're wrestling with a really fundamental problem in global conservation. How do you manage a resource if you don't actually know how much of it is left?
Yeah, that's the core issue.
We're talking about the crisis facing what they call data poor fish stocks. I mean, just imagine trying to manage this vital global resource. We're talking billions of dollars, crucial for food security. And you have less solid information than maybe a school science project sometimes.
That's a huge challenge. And that's the reality for, what, maybe 80% of the world's exploited fisheries? Something like that.
Exactly. So to tackle this, we're unpacking a really important 2018 paper. It's by Froese and his colleagues, titled A New Approach for Estimating Stock Status from Length Frequency Data. And this paper introduces a genuinely novel workaround called LBB.
That's right. So our mission today, really, is to understand LBB. That's the length-based Bayesian biomass estimation method. We want to see how this pretty simple concept, just measuring fish length, can provide the objective scientific foundation that fisheries management has, well, desperately needed.
And there's pressure for this now, isn't there, from regulations?
Oh, definitely.
Yeah.
It's driven by regulatory demand. If you look at things like the U.S. Magnuson-Stevens Act or the EU's Common Fisheries Policy, they demand science-based management for all exploited stocks. We can't really plead ignorance anymore just because the data is maybe too expensive or difficult to collect.
Okay, right. So let's unpack this. Standard, the traditional stock assessments, they're incredibly data intensive.
Hugely.
They need years of historical catch rates, fleet effort, independent surveys, tons of stuff. But even when you try simpler methods like stock reduction analysis, they still need a starting point, don't they? They need an independent estimate of the current biomass relative to the unfished biomass, that BB dollar Wilbur figure. Why is getting that initial BB dollar number so tricky? Why does it mess things up?
Well, it often comes down to subjectivity, or, even worse, circularity. To run a lot of the older models, you had to input a prior, basically an initial educated guess about the stock status.
Okay.
Now, if you rely on expert advice or just sort of conventional wisdom for that guess, well, critics can rightly say that the input heavily influences the final outcome.
Ah, right. It's like you're biasing the result before you even start.
Precisely. It's a bit like trying to weigh a fish, but you sort of nudge the scale towards what you already think it weighs. And what's more, the study points out that those earlier, simpler stock reduction methods, they often perform really poorly if that initial guess about depletion was actually wrong.
Which creates a catch-22, right?
Totally. You needed comprehensive data to know if your starting assumption was any good. But, well, if you had comprehensive data, you wouldn't need the simple method in the first place.
So the fundamental goal for Froese's team was to find an objective input, something cheap, easy to collect, universally available. And that metric is simply the size composition of commercial catches, what they call length frequency or LF data.
Exactly. I mean, think about it. Every port, pretty much every commercial fisher, they're already recording the length and size of their catch, more or less. That data is often just sitting there, maybe not used for complex modeling. LBB basically leverages that existing information.
Okay, this is where it gets really interesting for me. How does LBB actually work with just length data? Because when we talk about mortality Z, we're usually talking about a rate of disappearance over time. How do you get a time-based concept just from a snapshot of sizes?
Right, that's the clever part. It relies on a very elegant biological principle. Time is essentially encoded in size. LBB is designed for species, and this covers most commercial fish and invertebrates. They keep growing throughout their lives. The trick is to stop thinking about absolute time, years or months, and start thinking about relative life history stages. So LBB avoids asking those really hard, sometimes unanswerable questions like, what's the exact natural mortality rate, $1, or what's the exact growth rate, $2?
Right, those are notoriously difficult to pin down.
Very. Instead, it uses ratios. It estimates the natural mortality rate relative to the somatic growth rate, that's $7, and it estimates the fishing mortality rate relative to the growth rate, $5.
Ah, wait, so the time units? They literally cancel out in those ratios. Dollars per time, dollar involves length per time.
Exactly. You're left only with ratios related to length change.
That's clever. It sort of reduces this complex biological process down to its core proportional relationship based on size.
That's precisely the brilliance of it.
Yeah.
Because the fish is continually growing, the increase in length acts as a proxy for elapsed time. And by using these Emmett-Dollar-Vol ratios, the time units, and actually the biomass units too, they conveniently cancel out in the intermediate steps, which means the model isn't dependent on knowing the exact age of every fish. which, as you know, is often really difficult and time-consuming work. Autolith reading and all that.
Yeah, absolutely.
So using this length-based relationship, LBB estimates 5 key parameters simultaneously. You've got Leal Finter, that's the asymptotic length, the maximum size fish in that population generally reach.
Okay.
Then Lauf-Sifter, the length at first capture, where about 50% of the individuals are retained by the fishing gear.
Got it.
And then the mean MO dollars and the mean Fifter.
And to actually run this, they're not just doing simple algebra, are they? It's more complex modeling.
Oh, absolutely. It uses a Bayesian approach,
Yeah.
specifically a Monte Carlo Markov chain method, or MCMC.
Okay, Bayesian MCMC sounds powerful.
It is. Basically, it means the software they use, tools like JGS and R, runs thousands and thousands of simulations. It iteratively refines the possible values for those parameters until it reliably finds the set of values that best explain the actual length frequency data you fed into it.
And once it figures out those ratios, MLR and 5.
Then the current stock size relative to the unfished stock size, that crucial BB or $1, is calculated using standard, really well-established fisheries equations. Stuff dating back to Beverton and Holt in the 1950s and 60s.
Okay, so the theoretical framework sounds pretty solid. It's clever how it sidesteps the need for absolute time and uses those ratios. But, the real acid test for any new model is validation.
Definitely.
How reliable were the LBB results when they actually tested against stocks where the true status, or at least a well-accepted estimate, was known?
Right, the verification stage was pretty meticulous. They did it in 2 main ways. First, they ran LBB against simulated data. They essentially created artificial fish populations on the computer where they knew the true BB dollars, the true depletion status, because they'd set it themselves.
Okay, a controlled experiment.
Exactly. And LBB passed this test really well. The estimates of BB dollars it produced were not significantly different from the known true values. In fact, the true value was contained within the LBB's confidence limits in every single simulated scenario they ran. That's a good sign of accuracy.
That is encouraging. Okay, what about real-world fish?
So second, they applied LBB to empirical data, real data from 34 actual stocks. And these covered a huge range, different types of species, different life histories, different parts of the world. We're talking everything from tiny sprat and shrimp, like 7-centimeter max length.
Wow, tiny.
All the way up to big predators like cod and swordfish, reaching over 120 centimeters. They then compared the LBB results for these real stocks against independent estimates that came from full data-rich stock assessments, the gold standard, basically.
And what was the key finding there? Did LBB match up with the gold standard on that main goal, getting an objective measure of stock health, the BB dollars?
Yes, largely. This is really the core evidence for the method's usefulness. LBB estimates of relative biomass, BB dollars ones, were found to be similar to the independent estimates in 16 out of the 21 stocks where they actually had comparable data.
16 out of 21, that's about, what, 76%?
Yeah, around 3/4. And similar here means the 95% confidence limits overlapped. So this strongly suggests that LBB can provide objective, reliable, preliminary guidance on stock status using just that easily available length data.
That really does feel like a massive step forward, especially for fisheries managers in data-poor regions who previously had to rely on, guesswork.
Absolutely.
But I did notice a caveat in the paper. It seemed to work well for biomass, but maybe not so well for estimating fishing mortality. Why the difference?
That's a great catch and an important nuance. You're right. While the BB dollar estimates were robust, the LBB estimates of relative fishing mortality, FEF and Monde, tended to come out higher than the independent estimates, like F relative to FSME. So the paper's authors actually recommend that the LBB-derived Monde estimates should not be relied upon as accurate proxies for the current fishing pressure.
Okay, so why might that be?
Well, it seems to suggest that while the overall length distribution, the sizes of fish remaining, accurately reflects the cumulative result of fishing pressure, which is biomass depletion, the direct calculation of the instantaneous rate of fishing mortality, FFN and $I, through this specific length-only calculation might just be too sensitive or perhaps confounded by other factors to be trustworthy on its own.
Interesting. So focus on the biomass output from LBB, the BBB dollars, but maybe use other methods if you need a precise handle on current fishing effort itself.
That seems to be the practical advice, yes. Use LBB for the stock status assessment, the biomass part.
Okay, let's shift gears a bit and talk broader implications. Because one of the really fascinating things in this paper, I thought, was how it introduces a new indicator for stock health, one that goes beyond just, how many tons of fish are out there and looks at the actual biological structure of the population.
Absolutely. This is where the paper moves from just being about a statistical method to proposing a potentially powerful management tool. LBB estimates a specific length called lobdet. You can think of lobdet as the fish's kind of peak performance size.
Peak performance.
Yeah, it's the size where an unexploited group or cohort of fish would have its maximum total biomass. And critically, it's often the size where reproductive potential is also maximized.
Okay. So it's the size where that group of fish is contributing the most, both in terms of sheer weight and future generations.
Exactly. It's the size where a cohort provides the most value back to the population, ecologically speaking.
So if we can estimate that optimal size, we can then compare the actual average size of the fish being caught to that ideal size.
Precisely. The team proposes this new, theoretically sound indicator for judging stock health. The simple ratio, lactatos divided by little lost take. Right. And the logic is pretty intuitive. An exploited population where that ratio, LOP, is greater than 0.9, well, that population has a size and age structure that's pretty similar to a natural, healthy, unexploited population.
Okay, so 0.9 is the target.
That's the threshold they propose. It gives managers a clear, objective target for maintaining not just fish numbers, but an ecologically healthy population structure. This could help meet broader goals, like those in the EU's Marine Strategy Framework Directive, which talks about good environmental status.
That really connects the science back to, well, the fish themselves. If that ratio is low, say much less than 0.9, it suggests we're basically just catching the smaller, younger fish. Maybe the teenagers or even younger.
Essentially, yes. You're missing the larger, more productive individuals.
So when they applied this Lehman-Lupp indicator to those 33 real stocks they analyzed, what did the global health check reveal? Was it good news or bad news?
Mostly sobering news, unfortunately. It really confirmed the widespread nature of overexploitation, structurally speaking. They found that 61%, nearly two-thirds of those 33 stocks, showed what they termed truncated length structure.
Truncated meaning chopped off.
Yeah, chopped short. The population was effectively missing the older, bigger fish, the grandparents of the population, if you like.
Yeah.
Fishing was fundamentally altering the natural size distribution.
Wow, 61%. That's a lot.
It is. And maybe even more concerning, in 42% of the stocks, the catch composition consisted mostly of juveniles. The proportion of mature individuals in the catch was less than 50%.
So catching fish before they've even had a good chance to reproduce.
Exactly. It demonstrates pretty clearly that current fishing practices in many places are removing fish before they even reach their reproductive prime, let alone that optimal size little dot.
Okay, so it highlights the problem. But does LBB also offer prescriptive advice? Can it tell managers what to do about it, like how to set fishing gear?
It does, yeah. That's another practical output. LBB can calculate something called LC alta. This is the specific length at first capture, the size fish start getting caught, that would actually maximize both the catch weight and the remaining biomass for a given level of fishing pressure. It's like the ideal minimum size limit or mesh size target.
So it tells you the optimal setting for LEGALT.
Right. And crucially, the study found a strong correlation between their new health indicator, the LOAPT, and how close the actual LC-ALAs was to this optimal LC-APTA.
Ah, so if you manage to set your gear size closer to the calculated optimum, then the overall population structure, measured by LEGALT, gets healthier. It provides empirical confirmation that targeting a LEGALT is a practical management lever that directly leads to a better size distribution in the stock.
That link from the model's output to a concrete management action, like setting a gear size, must be really key for getting this adopted.
Hugely important, yeah. Okay, before we wrap up, we should touch on the limitations. Like any model, LBB isn't perfect. If you're relying solely on length data, what are the specific things or real-world events or biological quirks that could potentially throw the results off?
Good point. LBB is powerful because it's simple, but that simplicity relies on its underlying assumptions holding true. There are a few key limitations to keep in mind. The first big one is sampling bias. This is critical. The length frequency data you feed into the model must be genuinely representative of the exploited part of the stock the commercial fishery is actually catching.
Right, so no weird samples.
Exactly. If managers, say, only take samples from a nursery area full of small fish, or maybe from the nets of a small research vessel that uses different gear, that data will be biased. It'll likely skew towards smaller fish and could lead to really misleading, probably overly pessimistic estimates of depletion.
So the data quality and representativeness are paramount.
Absolutely. Managers need to ensure the LF data truly reflects the full-size range targeted by the commercial fishery. Second limitation relates to population dynamics. LBB assumes that things like mortality, growth, and recruitment are fluctuating around some average level over the period the samples were taken. It assumes relative stability.
Okay, but what if something unusual happens, like a huge boom in young fish?
That's the issue. Strong, sudden recruitment pulses a massive influx of new, small fish can violate this assumption. This is actually a weakness shared by pretty much all length-based assessment methods. They can struggle to distinguish between a big pulse of small recruits, which is generally a good sign for the future, and the heavy removal of large, old fish by fishing, which is a bad sign.
Because both scenarios result in a length distribution skewed towards the small end.
Precisely. So if you happen to sample during or just after a really strong recruitment year, the LBB analysis might give poor or misleading results about the current biomass status of the larger fish.
Okay, that's important context. And the third limitation.
The third one involves specific life history traits. LBB relies fundamentally on that length as a proxy for time idea, which works because most fish keep growing.
Yeah.
But LBB should not be used for those few, quite rare populations where the adults essentially stop growing altogether once they reach their maximum size.
Ah, like they hit a plateau and just live?
Yeah, sometimes they might live for decades after reaching max size, often by moving into deep, cold water where metabolism slows right down. If growth completely ceases, then length obviously stops being a useful proxy for age or elapsed time.
And the whole basis of the Emmental calculation breaks down.
Exactly. The calculation becomes invalid in that specific scenario. But for the vast majority of commercially important fish and invertebrates, they do exhibit indeterminate growth throughout their lives, so LBB remains applicable.
That clarity on the potential pitfalls is really crucial for anyone, like fisheries managers, looking to actually use this tool effectively.
Okay, so summing up, it feels like this LBB method provides a really powerful, objective, and importantly, low-cost way to get a handle on the health of many fisheries, especially those data-poor ones.
Yeah.
It shifts the conversation away from, sometimes unreliable expert guesses towards quantifiable metrics based on readily available data.
Absolutely. And that ratio, is particularly interesting. It's proposed as a potential new objective indicator, maybe even globally applicable, for assessing whether the size structure of a commercially exploited stock reflects a healthy population.
So more work needed there.
Definitely. Future research really needs to explore the full potential of this indicator. Test how widely it can be applied across different types of ecosystems, different management systems, see if it can become a truly standard global metric for assessing stock structure and sustainability. Well, that wraps up our exploration of the length-based Bayesian biomass estimation method, LBB, a really significant potential step forward, it seems, for managing our oceans more responsibly using data we often already have. Thank you for joining us for this deep dive.